Distance in statistics is measured in standard deviations. Length in the United States is measured in feet. Length in Canada is measured in meters. Weight in the United States is measured in pounds, while weight in Canada is measured in kilograms. Volume in the United States is measured in gallons. Volume in Canada is measured in liters. Any of these measurements can easily be converted to its counterpart. 1 foot is 0.03048 meters, and 1 meter is 3.28 feet. 1 pound is 0.45 kilograms, and 1 kilogram is 2.2 pounds. 1 gallon is 3.8 liters, and 1 liter is 0.26 gallons. These conversions are the same regardless of magnitude. Feet to meters doesn't change regardless of distance. Pounds per kilogram is the same for any number of pounds. Gallons per liter is the same no matter the size of the container. Statistics is different. Conversion factors change with every sample because both the average and the standard deviation change. Suppose we collect a sample of 10 muskie from the U.S. side of Lake Ontario. The average weight is 25 pounds, and the standard deviation is 10 pounds. These values can be converted to kilograms, as average 11.3 kilograms and standard deviation 4.5 kilograms. But suppose we get another sample of 10 muskie from the Canadian side. The average is 12 kilograms and the standard deviation is 5 kilograms. Converted to pounds, the average is 26.5 pounds with standard deviation 11 pounds. We still can't compare the U.S. sample to the Canadian sample, even if they are both in the same measurement units, because the average and the standard deviation are different. We need a measurement that works for all samples regardless of measurement unit. That measurement is number of standard deviations. Distance in standard deviations is called a z-score. A z-score of +1 means the observation is 1 standard deviation above the average. An observation 1 standard deviation below the average has a z-score of -1. Converting from a measurement unit to number of standard deviations is called standardization. We can compare any sample in any measurement units using z-scores. The conversion to number of standard deviations is distance between the sample observation and the sample average divided by the standard deviation. For the 15-pound muskie mentioned above, the calculation is 15 minus 25 divided by 10. The z-score is -1. The negative sign shows the 15-pound weight is 1 standard deviation below the average. In the Canadian sample, a 7-kilogram muskie is 1 standard deviation below the average. Z equals -1. A 30-pound muskie is 5 pounds above the average. 5 pounds divided by the standard deviation, 10, is 0.5. The z-score is plus 0.5, 1/2 a standard deviation above the average. A 14.5 kilogram muskie is 1/2 a standard deviation above the average. Z equals 0.5. A 15-pound muskie in the U.S. sample is in the same relative position to the average as a 7-kilogram muskie in the Canadian sample. The same is true for the 30-pound muskie and the 14.5 kilogram muskie. The two samples and equivalent z-scores for -2, -1, 0, 1, and 2 standard deviations from the average are shown here. Z-scores can be converted back to X values by rearranging the formula. We can use this to convert a sample observation to the average and standard deviation of another sample. For example, the July average daily temperature in New Orleans is 84 degrees Fahrenheit, with standard deviation 4 degrees Fahrenheit. The July average daily temperature in Montreal is 22 degrees Celsius, with standard deviation 2.5 degrees Celsius. How does a temperature of 24 degrees Celsius in Montreal compare to a temperature in New Orleans? A simple unit conversion of degrees Celsius to degrees Fahrenheit shows 24 degrees Celsius is equal to 75.2 degrees Fahrenheit. That's 9 degrees Fahrenheit below the average New Orleans July temperature of 84 degrees Fahrenheit. The weather in these two places is very different. A simple unit conversion won't work. Instead of converting Celsius and Fahrenheit degrees, we can convert using number of standard deviations. The z-score of 24 degrees Celsius in Montreal is 24 minus 22 divided by the standard deviation 2.5. The z-score is equal to 0.8. 24 degrees Celsius is 0.8 standard deviations above the average. By reversing the standardization, we can find the equivalent temperature in New Orleans. The z-score of 0.8 times the standard deviation of 4, plus the average temperature, 84 degrees Fahrenheit, which is equal to 87.2 degrees. Both 24 degrees Celsius and 87.2 degrees Fahrenheit are 0.8 standard deviations above their respective averages. This can be done for any July temperature in Montreal and New Orleans. The graph shows the Montreal and New Orleans temperature equivalent to z-scores minus 2, minus 1, 0, 1, and 2. For example, 80 degrees Fahrenheit in New Orleans will equal 19.5 degrees Celsius on the standard deviation scale. We can also reverse standardization to convert multiple samples to a common average and standard deviation. For example, Billy Bob and Mary Jo are both in the same freshman chemistry course, but in different sessions with different teachers. However, all the freshman chemistry teachers use the same exams. Billy Bob gets a 76 on the first exam, and Mary Jo gets a 74. Who did better, Billy Bob or Mary Jo? The class average for Billy Bob's class is 75, and the standard deviation is 12. Mary Jo's class average is 70 with standard deviation 8. Billy Bob's standardized score is 77 minus 75 divided by 12, which is equal 0.17. Billy Bob did just a little better than average. His grade for the test was 0.1 standard deviations above his class average. Mary Jo's standardized score is 74 minus 70 divided by 8, which is equal to 0.5. Mary Jo's standardized score is 1/2 of a standard deviation above her class average. Mary Jo did better than Billy Bob on the test because her z-score was higher. Suppose the chemistry teachers want to put all the classes on the same scale so they can assign grades. All scores are to be standardized to an average of 70 with standard deviation 10. Billy Bob's z-score was 0.17. On the 70 average and 10 standard deviation scale, his new score is 70 plus 0.17 times 10, which is equal to 71.7. Mary Jo's score is 70 plus 0.5 times 10, which is equal to 75. Mary Jo will have a higher grade on the new scale. Distance as number of standard deviations can be used to compare samples, put one sample on the same basis as another, and put multiple samples on the same measurement scale. All the problems of measurement units, averages, and standard deviations go away when samples are measured in the number of standard deviations.